Okay, welcome back to my, I guess, chemistry lectures. What we're going to be going over right now is nucleophiles. So this is, we've heard a lot about this, uh, nucleophiles. And nucleophiles are species that want to donate electrons to and this should make sense, to a positively charged nucleus. So that's why it's called a nucleophile, right? The nucleus is where all the protons are contained. The nucleus is always positively charged. And nucleophiles means that they're attracted towards the positive charge. They want to donate electrons to a positively charged nucleus. So basically, there's a few rules for nucleophiles, but we're not going to go into them too much because in IB we don't need to necessarily be able to compare nucleophiles and protic versus aprotic solvents, because typically what we've already talked about, right? Already talked about fluorine, we've talked about chlorine, we've talked about bromine, we've talked about iodine, basically as leaving groups, and basically how these work as leaving groups. But what we didn't talk about is how they necessarily compare to one another, right? We talked about a hydroxide ion coming in most of the times, and the hydroxide ion is a very strong nucleophile, so it's a stronger nucleophile than all of these. So, of course, hydroxide is going to be better than all of these, but then how these compare to one another, we don't need to know that for IB chemistry. So that's why I didn't really cover it in the last video, how a protic versus an aprotic solvent changes the nucleophilicity of different halogens against one another. Basically, I just compared hydroxide. Why we said that, for SN2 react or SN1 reactions. Oops, sorry, that's supposed to be chlorine. Carbon, carbon, carbon. Just imagine these are all methyls, and that this is a tertiary carbon. We said that this is a better leaving group as long as we've got a polar protic solvent, because the protic solvent can help solvate this halogen in solution, and that the better nucleophile can come in and attack once he's gone. But what you start to see in more advanced organic chemistry is that when we start to compare, if we had chlorine as the leaving group, we had chlorine as the leaving group, right? And fluorine came in, what would be the better nucleophile in this case? Or if bromine came in, what would be the better nucleophile in this case? And what we realize is that a protic solvent nucleophilicity is different than an aprotic solvent. So don't worry too much about that. If I read through and there's any questions that come up on that, we're going to cover that. But I'm pretty sure I'm certain that the book didn't mention at all how to compare the reactivity of chlorine versus bromine versus fluorine. Okay, so basically what we're going to cover then, we're just going to cover the basics of nucleophiles and what you need to know. So what nucleophiles are is they're electron-rich species that are capable of donating, and this is the important part, donating a pair of electrons. So what we called that, back when we did Unit 2 and Unit 4, we called that a dative covalent bond. Or later on in your acid-base unit, we called that a Lewis base, something that's capable of donating a pair of electrons. If you accept a pair of electrons, you're a Lewis acid. So lots of questions if you ever see it, which one would be a better nucleophile? you basically need to check for the ones that have a pair of electrons. So once you draw out the Lewis structure, if there's no lone pair of electrons, it is not a nucleophile. So you can scratch that out. So that's rule number 1 of what you need to be a nucleophile. You need to possess a pair of electrons that you're willing to donate. And the second rule that you guys need to know about nucleophiles is that negatively charged ions are better nucleophiles than their conjugate acids and their conjugate acids. So that's just kind of like saying, if we were to compare H2O and OH, right? So OH has a much more electron charge density and overall negative charge. And it's got more electrons than it previously had before, so it's got a net formal charge of -1. So the oxygen has a net formal charge, so he's willing to donate electrons more easily than oxygen in water, where it doesn't have that net charge. So if it donated the bond, it would change its charge. So if you imagined, right, you just had like a OH and some sort of carbocation. So let's just say a tertiary carbon. CH3, CH3, H3. A carbocation. If he was going to donate to this, right, he's got 1, 2, 3, 4. He donates that pair of electrons. And our final structure, right, CH3, 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 O, H, H, and he's got a lone pair. If you calculate the formal charge of this oxygen right here, let me just change the color to draw that lone pair. You calculate the formal charge of that oxygen. Oxygen typically has 6 electrons, minus half of the electrons in a bond, 1, 2, 3, minus 3, minus lone pair electrons, minus 2. Oxygen's got a formal charge, of +1. So a formal charge of +1 on a very electronegative atom, he's very unhappy about that. Whereas when he donates his pair of electrons, he gets a formal charge of 0. So this one is a better nucleophile than water when we're comparing the two. So on the next page, let me just erase this off. I'm just going to show you a little bit what I mean. So if we looked at, I saved this right over here. If we look at these different groups, right, basically we said that iodine was a very good leaving group. It loved leaving because it was stabilized in solution by that hydrogen bonding and by the polarity of the solution. Bromine was a little bit less so. Chlorine was a little bit less so. Oh, it's working. Nice. Okay, chlorine a little bit less so. And we just, we compared them as leaving groups. This one we said, right, could be a good leaving group. And we said that because resonance, right, we take that, I'm just going to draw the whole chain just as an R. O, O, single bonded to an O. This can donate that pair of electrons in, and he can come out and get the negative charge. And he could donate it back in, and it can come out here. So it's got a resonance structure. Since it has a resonance structure, it is a good leaving group. Then we get down here, and we get, the stronger the base, as we said before, the weaker the base, the better the leaving group. So the stronger the acid, the better the weaker the conjugate base, and the weaker the conjugate base, the better the leaving group. You've got water that's conjugate base, the hydroxide, which is a poor leaving group, right? It's a strong base. Hydroxide is a strong base, so it's a good nucleophile. So it's kind of the opposite, right? Whatever's a good leaving group does not make it a good nucleophile. So in this case, iodine is not a great nucleophile. Bromine, not a great nucleophile. As soon as we get down to the bottom, we've got very, very, very good nucleophiles. They form very stable structures, and they're very poor leaving groups. So basically, if you can, there's a nice Khan Academy video on nucleophilicity versus basicity, and also one just on nucleophiles. And what you're going to see is that the trends that we just talked about. So it depends on whether they're in a protic versus an aprotic solvent. But that's more in depth than we need to go. What we need to know basically is that the conjugate base with the charge is a better nucleophile than the conjugate acid with no charge. And that's basically as far as you need to go into it. If you'd like to read into it a little bit more, of course, I highly encourage that. And you could see why, in some cases, fluorine can be a very good nucleophile. It can be a much better nucleophile than iodine. But then we'll see, when we change the solvents, all of a sudden fluorine is a much worse nucleophile than iodine. And it all depends on the solvent. So it also depends on the leaving groups. Iodine is a good leaving group in a protic solvent, but is it a good leaving group in an aprotic solvent? Bromine, good leaving group. You can compare these, and you'll see that as we go more in depth, you're going to see these rules change a little bit. But luckily for you, not luckily for you, but in IB, what you just need to know is just a little bit about the basics. This is a better nucleophile than this. This is a better nucleophile than this. This is a better nucleophile than this. So just by following the rules. So basically the negative charge equals a better nucleophile when compared to its conjugate acid. And also just that nucleophiles need a lone pair of electrons to donate. So okay, so that's about all you need to know about this. If we do need to go into a little bit more depth, don't worry, I'll make another video on it. But hopefully this made a little bit of sense, and you can tell what is a nucleophile now. If the question shows you something without any lone pairs, you can say nope, it's absolutely not a good nucleophile. If it shows lone pairs, okay, it's a good nucleophile, or it is a nucleophile. And then if you just start to learn a little bit about this graph, we can see which one would be a better nucleophile, right? Hydroxide versus iodine. And fluorine, we always see this as exception here, just because that strong bond, since it forms such a strong bond with carbon. So okay, hopefully this video helped. I'll see you next time.